Okay, class, I think we're recording here. Hopefully we are. Okay, Friday, April 3rd, right? Moving on into chapter 10. Right. Last time we did lumped matching, and there's a homework out there on that and a video and some notes. So now we're moving into the next section in chapter 10, which is scattering parameters, right? So scattering parameters are basically techniques for characterizing microwave devices. Okay, so they're important. It's a good idea to have an understanding of this material. And so, right here we have, some network. You don't know the details of that, and then we'll specify the details and find the scattering parameters for some different networks later. And then here, right, we have the source located here. The source is connected to the microwave network via transmission line of some characteristic impedance Z naught. And then similarly on this side, there's a load, right? And that load is connected to the microwave device through some characteristic transmission line with characteristic impedance Z naught, right? So, right, the scattering the scattering matrix representation is in terms of voltage waves, okay? So we have a forward voltage wave at this port, right? So this is a so-called input port, and this is or rather port 1, and this is port 2. And so at this point, there's a forward traveling voltage wave and a back traveling voltage wave. Similarly, over here, there's a forward at port 2, there's a forward and back traveling voltage wave. And so there's subscripted plus for forward and minus for back. And then the subscript, or rather superscript plus and minus for forward and back, and then subscript 1 for port 1 and 2 for port 2, etc. Right? So V1 plus is the voltage wave entering port 1, V2 plus would be the voltage wave entering port 2, V1 minus would be the voltage wave leaving port 1, etc. Okay. So, right, some of the, in general, depending on the network specifics, right, depending on what this might be, a transistor, it might be passive elements, it might be reactances. You don't know what necessarily is inside this box yet, but we'll specify that as we proceed through and look at different examples. Right, so some of V1 plus, right, some of this forward wave is reflected at this port, depending on the impedance discontinuity here at the frequency of operation. And some of this is transmitted out to port 2 and contributes to V2 minus at port 2. Okay, so in general, what you have, right, is the wave exiting port 1 is proportional to the wave entering port 1 and the wave entering port 2. And so these proportionality constants really are referred to as our scattering parameters, right? So you get V1 minus is S11 times V1 plus. So S11 is the amount of incident wave that reflects at port 1 contributing to V1 minus, and V1 minus is contributed to by V2 plus, right? Some of it makes it through the network and contributes to V1 minus, and the amount of that is the scattering parameter S12. Similarly for V2 minus, right? So we can organize this stuff in a matrix. So right, these are the so-called scattered voltages, right? These are the voltages incident on the ports, and then this is the scattering matrix. Right, so if we want to get, and this becomes important right here, right? This little observation right here. If we want S11, how are we going to be able to measure that? Well, clearly up here, right? If we come back to this statement, then S11 is going to be V1 minus divided by V1 plus, provided V2 plus is 0, right? So if you set V2 plus to 0, that goes away, and S11 is just going to be V1 minus over V1 plus. So we say that S11 is V1 minus divided by V1 plus with V2 plus equal to 0. Well, how do you get V2 plus to be 0, right? Well, one way to do that, right, would be to terminate, right, this transmission line in its characteristic impedance. Because if that's the case, any any voltage incident on the load would be completely absorbed by the load. None of it would be reflected, right? So we can get V2 plus to be 0 by terminating port 2 in its characteristic impedance. Okay, so that's how we're going to compute S11 in a minute. So keep that in mind. And so the general case, right, any particular scattering matrix element that I want, Vij is going to be Vi minus over Vj plus, with all the other Vk pluses be equaling to 0, except of course for Vj plus. Okay, so this is just a general statement of what this was a specific example for, right? So we'll want to compute V21 and V12 as well. Right? And so in so doing, in order to set these other incident voltages from the other ports to 0, you're going to have to terminate those ports. Again, that's how you achieve this. And in general, these the scattering matrix elements are complex numbers, right? Some amplitude and phase. Okay, so scattering parameters, right? Scattering parameters, important. It's important because that's how we describe microwave networks. And we'll mention in a minute, toward the end of the presentation here, the discussion, that the network analyzer, right? It represents a microwave network in terms of scattering parameters. So the network analyzer will actually measure S11, S12, S21, and S22 over a range of frequencies, right? And there's different ways to display that using the network analyzer. But we'll say a little bit more about that in a little bit here. Okay, so as usual, right, what do we want to do? We need to work an example to get a little better understanding of this, right? So this is just example 10.5. You can follow this in the text, or you can follow my notes as well. Right. A couple of different places to get it. Okay, so here's a 50 ohm transmission line, right? And it's connected to a simple microwave network, just a 100 ohm resistor, right? And then on the output side of this microwave network, if you will, is another 50 ohm transmission line, right? So we want to compute the scattering matrix at these two ports. Right? So V1 minus V2 minus S11, S12, S21, S22, V1 plus V2 plus. So here's our scattering matrix for this particular microwave network, and we're trying to determine what the scattering parameters are for this network, right? So let's get S11 first, right? So S11 is V1 minus over V1 plus with V2 plus equal to 0, right? So in order to make V2 plus 0, right, I need to terminate the transmission line over here in its characteristic impedance. So we're going to terminate port 2 in 50 ohms. Well, if we put a 50 ohm load here, right, then since the characteristic impedance of the line is 50 ohms and the load is 50 ohms, then looking into this port right here, you see 50 ohms looking back that way, right? So the transmission line on the left sees, this 50 ohm transmission line on the left sees the 100 ohms here and the 50 ohms here, right? Because we're trying to find S11. Right? So the reflection coefficient, right, V1 minus over V1 plus, basically the reflection coefficient at this point is just going to be the impedance here minus 50 over the impedance looking into this point plus 50. The impedance looking into here is obviously 100 in series with 50, right? So S11 is 50 minus 50 over 150 plus 50, right? Or 100 over 200 are half, right? So S11 then, real quickly here, we're able to determine that is simply 1/2, right? Now, by symmetry, right, if I repeat the exercise, right, and try to find S22, that's just going to be the reflection coefficient at this point with this port terminated. Well, I'm just going to repeat the steps that I just completed. And so clearly, because of symmetry, right, S11 is equal to S12 is equal to 1/2. Okay, right. So 2 of the 4 scattering parameters have been determined. So we need the other 2. So we got the diagonal, we need the off diagonal terms. Okay, so, right, so what is S21? Well, it's, according to the definition, it's V2 minus, right? So it's the voltage wave headed in this direction divided by the voltage applied here, right? Forward voltage applied here with V2 plus 0. So again, we're going to have to terminate uh, we have to terminate the transmission line here in its characteristic impedance so that we ensure that the voltage coming back in here is 0. Okay, so that's going to look like this, right? Our Z naught, 50 ohms, right? Series with 100 ohms, and here, right, 50 ohms. So what we need, right, is this voltage right here. Well, we've already computed, right, the reflection coefficient here. And so that's the wave headed this way. If I take 1 plus that reflection coefficient, that's going to give me the transmission coefficient at this port, right? Right here. So we found that above, the reflection coefficient was 1/2. And so the transmission coefficient is 1 plus the reflection coefficient, or 1 plus 1/2, which is 3/2, right? Now, that's the wave headed to the right at this pair of terminals, but we want the voltage here, right? And so that forward wave is going to divide like a voltage divider between the 50 and the 100 ohms. So it's going to be transmission coefficient, 3/2 times 50 over 100 plus 50, right? Voltage division. So 3/2 times 1/3, which is 1/2. And so again, by symmetry, so we found S21 to be 1/2. So by symmetry, if I turn the problem around, it looks exactly the same. So S21 is going to be equal to S12. So in this particular problem, right, it turns out that all the scattering parameters are the same. So it's 1/2, S11's 1/2, S22's 1/2, S21 and S12 are halves. And so you could write it as 1/2 times the 1111. Okay. So pretty straightforward, right? It's a little bit of what's required here, right? It's you have to have some understanding of transmission line theory to calculate the scattering parameters, right? And you need to understand this concept, right? That Sij is Vi minus over Vj plus, with Vk being 0, right? And we make that 0 by terminating the port in its characteristic impedance. That's how we set that positive traveling voltage to 0, right? We set Z load equal to Z naught, and that eliminates any reflections here. If there's no reflections here, then V2 plus must be 0. So keep that in mind, right? That's the essence of how these problems are solved. Okay, so we did this simple example, right, of a microwave network consisting of 100 ohm series resistance. We worked that problem. Now let's work another one, maybe somewhat more complicated. Okay, so we're going to get rid of the symmetry this time, right? So our microwave network is right series 25, shunt 50. So looking this way, we don't see the same thing as we see looking back in the other direction. So we actually have, in this case, 4 calculations to do. Okay, so let's get S11, right? What is S11? It's going to be essentially the reflection coefficient at this point in the circuit, right? Which is Zn minus 50 over Zn plus 50, right? Where Zn is the impedance that I see that this transmission line sees with, right, this port terminated. Why did you terminate port 2? Because you need to make sure that V2 plus is 0, right? This guarantees that V2 plus equals 0, okay? So if we terminate this in 50, this transmission line in 50, then looking into this point is also 50 ohms, right? So I've got 50 in parallel with 50. So it's 50 in parallel with 50 in series with 25, right? So the load that this 50 ohm transmission line sees is 25 plus 50 in parallel with 50. So 25 plus 50 in parallel with 50. And so the reflection coefficient is that minus 50 over that plus 50, right? So 50 in parallel with 50 is obviously 25. 25 and 25 is 50. So it's 50 minus 50 over 50 plus 50, which is 0, right? So in this case, because of the conditions of the circuit, uh, whatever, there is no there's no no reflection of the incident wave at port 1, right? Because S11 is 0. Okay. So what is S21 going to be, right? We're going to use the same approach that we used on the previous problem. So we're going to multiply the transmission coefficient, right? That'll give us the amount of the wave headed in this direction. And then we have to figure out how much of that is delivered here, right? Well, that's going to be how much of that is delivered to the 50 in parallel with 50, 50 ohms in parallel with 50 ohms, right? So it's going to be T, right, which is 1 plus gamma. Well, 1 plus 0 is going to be 1 times 50 in parallel with 50 over 25 plus 50 in parallel with 50. Okay, so that's going to be 25 over 25 plus 25, which is 1/2. So the transmission coefficient S21 times the transmission coefficient is S21 times this voltage divider, right? This is just a voltage divider. This over this plus that. What is this? It's 50 in parallel with 50. Why is it in parallel with 50? Well, because we had to ensure that V2 plus was 0, and so we had to terminate port 2 in 50 ohms. Okay, so you hopefully getting an understanding of this. Pretty straightforward. Okay, now let's turn it around and get S22, right? So now we need the reflection coefficient looking into this side, right, with this port terminated. Right? So if we terminate the port on the left in 50 ohms, then then looking back in this way, we see 50 ohms, right? And so, right, what we need to figure out what we see looking into into port 2. What impedance we see looking into port 2. Well, that's going to be, right, 50 plus 25 in parallel with 50, because we terminated this in 50. It's a 50 ohm transmission line. So right here is also 50 ohms shunt. And then that is in series with 25, right? So that's 75. So I need to put 75 in parallel with 50. And that's the impedance that this line sees at that location. And so the input reflection coefficient at port 2, which is S22, is going to be 75 in parallel with 50 minus 50 over 75 in parallel with 50 plus 50, or 30 minus 50 over 30 plus 50, which is minus 1. Okay. And then using the same procedure, right, S21, right, again, we terminate port 1 is going to be the transmission coefficient, right, which is 1 coefficient, times, in this case, right, we're going that way, so it's going to be, this 50 doesn't enter into it because it's in parallel, right? So it's going to be divided by plus that impedance. That's going to be the voltage divided in that direction. So it's T times 50 over 50 plus 1 plus S22 times 50 over 1, S1 is a fourth, so fourth times 2, or a half, right? So finally, then we get the scattering matrix for, a somewhat more complicated case. Okay. So in every case so far, right, how's this work? Well, we get the reflection coefficient here or here with the port terminated. Then we can use that, then define the transmission coefficients, S12 and S21. We take that reflection coefficient and find the transmission coefficient associated with it, and then we take that T and then use a voltage divider typically to find S21 and S12. So, right, reflection coefficient. Once we get that, find the transmission coefficient times the voltage divider. Reflection coefficient, that gives us the transmission coefficient times the voltage divider. Okay, so that's how these types of problems unfold. So pretty straightforward. Pretty straightforward. Takes a little practice. Okay, a couple of other definitions that are important to us in microwave network description. One of them is return loss. The other is insertion loss. Right. So what do we mean by return loss? Well, we define that as minus 20 log base 10 of V leaving a port divided by V entering a port. Right. Port I. Right. Well, that's just going to be the reflection coefficient at that port. So the return loss is simply a microwave parameter that's the log proportional to the log of the reflection coefficient at a given port, right? So, right, if the reflection coefficient is 0, right, the return loss is going to be infinity, right? Because the log of 0 is minus infinity, and then you multiply by minus 20, and that's going to be positive infinity, right? So a high return loss means that nothing is reflected, right? On the other hand, right, if the reflection coefficient at a port is 1, right, then the log of 1 is 0, and so the return loss is 0, which means that everything is reflected, right? So very often, right, we don't want any reflections, and so in this case, big is good, generally speaking. Not always, but generally speaking, a large value of return loss is desirable. Right? So if I'm feeding an antenna and I want it to work at a certain frequency, then I don't want any energy reflected from the input to the antenna at that frequency. And so I would desire a large return loss at the design frequency. So very often when you're analyzing antennas, right, you'll use a network analyzer and you'll measure S11, say, the input reflection coefficient looking into your antenna, and you'll express that as a return loss, and it would just be a menu that you punch a button and then hit magnitude or hit dB, and it would express it in return loss as a function of frequency. Right. So, right, insertion loss, as the name implies, right, is going to measure how much signal is lost in going from port I from port J to port I. Right. So it's the amount reflected out of port I that's fed into port J. Okay, so how much of the signal is lost as it goes from port J to port I? Attenuation resulting from insertion of the network between the source and the load. So in our example previously, right, here's the source side, say, here's the load side. So how much attenuation uh, do we get, right? Well, in this case, right, we determined that the return loss, right? Yeah. For example, here's the sorry. Let me restart. Let me start that over again. In any event, the right. Let's go back and look at the microwave network that we just completed, right? So we had, in that case, page 3, right? It's the scattering matrix for this is 0, 1/2, 1/2, minus 1/4, right? And so the return loss at port 1, right, is going to be minus 20 log of 0, which is infinity, right? So, right, so uh, no signal is returned, and so all of the returned is lost. That's you have to think about the words for a minute. So typically that would be good, right? And the return loss at port 2, right, looking back in this direction, right? In this direction, the reflection coefficient was 0 looking into this port. In this direction, the reflection coefficient looking into here is minus a fourth. So when we take minus 20 log of the magnitude of that, we're going to get 12 dB, right? So in that case, then uh, the return loss into this port is 12 dB. Right? So in that case, right, what that means essentially is not much of it's reflected, but a little bit is. Right. That's what that says. Okay, and insertion loss, right? In that case, they're both a half, and so it's going to be minus 20 log of half, which is 6 dB. So in going from, if I apply a signal here, the signal that comes out is essentially 6 dB down from the signal that I input here. Similarly, if I apply a signal on the left-hand side, the amount transmitted in this direction, right, is 6 dB down. So we say the insertion loss of the network is 6 dB. Okay, so right, this is kind of hitting the high points of this section. Now you're going to need to go back and read that carefully and compare these notes uh, to Stu's presentation and make sure you get the ideas here. So mainly what I've done is to try to walk you through a couple of examples to show you how to work these types of problems. Hopefully that's the value of this, right? A couple of other sections, right? Shifting the reference plane, that's important. So what's that about? Let's, let's look at it. Um, Back up here. So we know the scattering parameters at one position in the microwave network, and if we may want to know those at another position in the microwave network, right? And so that brings us to this section right here, right? So the idea is, hey, I know I know V1, the relationship between V2 minus here. What is I guess that should be V2 plus entering. I know V2 plus here. What is V1 plus over here, right? So it has to, you have to propagate, what we say is you have to propagate this wave back to this point, right? So so V2 minus, right, is V1 plus e to the minus j beta L, right? So this wave propagates from here to here. I guess this is V2 minus. Maybe I'm not paying attention. He labels this as V2 minus. So again, V2 minus is going to be V1 plus propagated from this position on the transmission line to this position, right? So this is a plane wave, and that's our phase constant. So it propagates e to the minus j beta L, right? So S21 is V2 minus over V1 plus, right? And so that's just going to be 1 e to the minus j, right? So the upshot of it is, right, if you know the scattering matrix at port 1 down here and you want to know the scattering matrix over here, you simply uh, multiply by this port shift matrix, right? And in so doing, you end up with this representation. So it's the same scattering parameters you had before, but now there's a phase shift associated with them of 2 beta, right? In the case where S11, it's L1, and in the case where it's S21, it's L1 plus L2, right? Because these propagate from here to here, and then it propagates from there to there. So I think that's pretty straightforward. Right? Uh, so, right, and then lastly, right, this little section on network analyzer, right? So this is, of course, what a network analyzer looks like. So it's got a port here and a port here. So here's a cable going from port 1 on the analyzer to the device under test, usually referred to as a DUT, right? Device under test. And then out of the device under test to port 2, right? This other wire is probably just some sort of DC signal that's biasing up this transistor or whatever's in this microwave network, right? And so, what does the network analyzer do? Well, it measures the reflection coefficient at right. What do you want it to do? You want it to measure the reflection coefficient right here and transmission coefficient at this port, looking into the device under test, and the reflection coefficient and transmission coefficient at this port, looking into the other side of the device under test, right? And so, right, it's going to measure that at this port, right? So you have to take out or take into account these cable lengths. And so the way you do that is you typically remove the device under test and you put known loads on this port and this port. For example, you'll calibrate the analyzer, put a short, open, and through, right? A short on this port, an open on this port, a short on this port, an open on this port, and you connect just a simple 50 ohm transmission line between the two ports. Each time you do that, you tell the analyzer you've done it and you punch a button and it records the response of these known calibration uh, elements. And then once it has all that data, uh, then you hit done cal, and then when you put your device in there, it'll actually measure and present the scattering matrix associated with the device itself at the ports looking into the device, right? So there's a calibration process that has to take place there, and Stu describes that, right? So there's plenty of network analyzers around the department, so hopefully you'll have a chance to use those while you're progressing through your career. Okay. All right, that's all. That's really all I had to say for today. So that kind of wraps us up on this presentation on scattering parameters, right? So go ahead and work homework number 24. Homework 24 will be problem 1027 and 1031, right? So these are odds, so I think you're going to have answers to those in the back of the book. All right, very good. That completes the discussion for today. Shut this thing off.